Okay, we're now going to talk about Chapter 9, Section 1, the Introduction to Hypothesis Testing. Hypothesis testing is the last major concept in the course. For the rest of the year, we're going to be doing hypothesis testing and confidence intervals pretty much. And so then aside from that, just reviewing what else we've done. And really, we've been sort of hinting at hypothesis testing for a while now. As a matter of fact, coming up with the actual p-values as we're going to, we did that in Chapter 7. And so let me make that connection again in regards to sampling distributions. And hopefully after this chapter, you'll have a better understanding of how sampling distribution relates to statistical inference. So hypothesis testing, otherwise known as tests of significance, that'd be sort of the same thing. So what's going to happen in a hypothesis test is there's always going to be some form of claim in the problem, some sort of statement that we are going to consider our null hypothesis. And so, for instance, like let's say if there's a company and it is previously there was 20%. We'll go with a proportion first of all. 20% of the employees there were dissatisfied with the parking situation, let's say, and so they've decided to test this to see if it is still valid, if it is still 20%. And so we're going to call this our null hypothesis. And we'll write this out a little more formally in a minute, but that's going to be our notation in this chapter. And it is felt now that maybe this value has gone up, maybe that more than 20% feel that of the employees feel that they are not happy with the parking situation. So this thing here is the alternative hypothesis. And so there's our null and there's our alternative. Now in Chapter 7 what we did is we would take a sample. Let's say if we took a sample of 200 employees. Of course we're assuming that there's at least 2,000 employees for our population size to be at least 10 times our sample size. And let's pretend that 50 of those 200 randomly selected employees now say that they are dissatisfied with the parking. So that would give birth to my p hat, which is x over n. So this is my sample statistic, which I care about. And so that is 0.25. Okay? So which is certainly different from that. But the question is it statistically significantly different? Or is it plausible that this difference is due to sampling variability? It looks like it may have gone up, but maybe that difference is just due to chance. And so what we did in Chapter 7 is we had the concept of a sampling distribution. And that was this. If we assume the null hypothesis is true, if we assume this 20% figure is right, here's what my sampling distribution will look like. It'll be centered around 0.2. Okay, and so the one we got here, well, we need to know our standard deviation to see exactly where that is. And as you may recall, the standard deviation is going to be equal to the square root of 0.2 times 0.8 over 200, p times 1 minus p over n, and that is equal to 0.028 approximately. And so what we have going on here is a sampling distribution is every value p hat could possibly take. So 0.25 is somewhere up here. But if we were to take another sample and get another p hat, we would get another p hat. And if we took a third sample, we get a third p hat, just like we talked about in Chapter 7. So this is every possible value p hat could possibly take. And whenever we take a sample, you should always visualize this sampling distribution. You should say to yourself, this p hat is one of many I could have gotten. And so the question we're going to ask in this chapter is, assuming that this is the sampling distribution and the p hats really are centered around 0.2, what's the probability we would get 0.25 or more? All right, and so one standard deviation up here, that's going to be right here at this inflection point, halfway down the hill. So that would be 0.28 above it. So this would be 0.228 is where that is. So 0.25 is going to be somewhere up here. And so we are going to find this area. And so then there's 0.25, our sample value. And so the question we're going to answer is, given this 0.2 figure is correct, what is the probability that we will get I almost put an x bar. This is a p hat. Of course, x bar is going to be later in the chapter. P hat is greater than 0.25. What's the probability our p hat is going to be greater than 0.25 if you were to randomly select one of these p hats? And we could find this using normal CDF. So if we said normal CDF, And then from 0.25 to infinity, finding the area here of the shaded region, 0.25 to infinity. Our mean of our p-hats is 0.2, and our standard deviation is about 0.02828 actually. So that is my lower bound. That is my upper bound. This is the mean of my p-hats. That's the standard deviation of my p-hats. And this, in fact, is equal to so what it is, I need to find it. So this, in fact, is equal to 0.03855. And this, in this chapter, and we actually called this in chapter 7, that's a p-value. That is the probability that, assuming the null is true, we would get a sample value this high or higher. Okay, and the reason we go higher is because our alternative is greater than. We'll talk about all that. And so that is this area there. That is our p-value. It is the probability we would get a sample value this unusual. And in general, what we're going to say is this, is if this number is low enough, if it's a low enough probability, it would cause us reason to doubt this, or what we're going to say is reject it. And since this value is less than 0.05, okay, in general, that's our general rule of thumb. This would be our alpha value. We would reject the null hypothesis in favor of the alternative. And so that's going to be our conclusion of our hypothesis test that we're going to do, is we are going to say this p-value is below 0.05. That gives us a reason to reject the null hypothesis. It appears, and then say we have convincing evidence that P is greater than 0.02. In other words, we have convincing evidence that the proportion of employees that are dissatisfied with parking is now above 0.02. That is the premise of what we're going to do, in essence. But we're going to do the same thing, in essence, sort of we did in Chapter 7, except we're going to add on some notation and write a little mini essay. We're going to write our hypotheses. We're going to make sure we're getting good data. How did you get these 200 people? You better have gotten them randomly. Do we have independence? Do we have normality? All that stuff. And then come up with our p-value, just like we did there in our test statistic, as we'll talk about, and then state our conclusion, which is exactly what I just said. All right, so I think the easiest way to learn this stuff is hopefully to go through a hypothesis test. Section 1 is just the terminology, much of which I just said in here we're going to formally define now. Section 2 is doing a hypothesis test with a proportion, which I sort of did here. And then Section 3 is doing a hypothesis test with a mean. So we would be working with mu's, with mu in our hypotheses, and working with x bars, our statistic. And that's also similar to what we did in Chapter 7. So let's go ahead. And so here's the little note sheet. And I'm going to go ahead, we're going to do this hypothesis test. And then as we go through it, we've got some definitions such as null hypothesis, alternative hypothesis, and so forth that we're going to formally define, that you have to know what these things are. But I think the main way to understand what these things are is to see them in context, like problems like this, and seeing enough examples to see how they apply in different situations. But anyway, so okay, so here we go. So in this situation, it says, each week a large truckload of tomatoes arrives at McGill's tomato sauce factory. He takes a random sample of 300 tomatoes. Aha. That means we've got a condition of randomness met, and that looks to be a pretty good sample size. But we'll see. Let's see. On one particular week, to do quality control, he finds that 38 of them have flaws. Okay, so 38 out of the 300, that smells like a p-hat. It sounds like a proportion that are flawed, and it doesn't look like a mean, which is going to be Section 3. If he has statistically significant evidence that more than 10%, okay, so there's our percent, which is the same thing as a proportion, more than 10% of the tomatoes are flawed, he will reject the whole truckload. Perform a significance test using alpha is equal to 0.05. So what that means is our p-value we're going to get, if it's below 0.05, we're going to reject the null. Okay. Also, define type 1 and type 2 error in this context, and make sure you understand the terminology that goes with the test. What would the p-value be in a two-sided test? So we're going to talk about all of this terminology, type 1, type 2 error, in a two-sided test, and so forth. Well, whenever you're asked to do a test of significance, you will have to use the THAME acronym, and that's just an acronym that I came up with. I mean, every AP Stats teacher comes up with something, but you have to write a mini essay that has these 5 parts that you'll be graded on. So make sure you understand how to do each of the 5 parts, and each of the individual parts really aren't hard, but make sure you remember to do each of them or it will be counted off, and you could be asked about each of them. So the first thing is, what is our type of inference? A lot of this is similar to confidence intervals, and so we're going to have 2 more types of inference in this chapter, and the one in section 2, which is this one, this is going to be a 1 proportion, so a 1 proportion Z test. You remember in section 8.2 we did a 1 proportion Z interval. Now we have a 1 proportion Z test. There, that's 1/5 of it. You get 1/5 of it right. The next thing, and this will be new this chapter, we have to write our hypotheses. Whenever we're doing a test of significance or a hypothesis test, we're going to come up with our hypotheses. And first of all, we're going to have our null hypothesis. And the way we're going to write that is this. Our notation is H sub O colon, and then we're going to, in this case, it's going to be P is equal to 0.1. The null hypothesis is whatever is claimed as true or whatever has been previously true is continuing to be true. It is the status quo, all right, in essence. So here it is 10% or 0.1. All right, and it's always going to look like this. And in section 2, it's always going to be P is equal to some proportion. All right, or in section 3, it's going to be mu is equal to. There's never a greater than or equal to there. Now, our alternative is what we suspect might be true or what would call for a change or difference. And the alternative here, it says, let's see, if he has statistically significant evidence that more than 10%, so that is what we're leery of. That's what we're testing for. That's what's going to be an issue, is if it's more than 10%. So we're going with greater than there. All right, and so that's how you write your hypotheses. But whenever you write a variable or a letter, you have to define what that is. So whenever you write P or mu here, make sure and define it. And so P is the proportion of all the tomatoes. And in this case, we're worried about the tomatoes on this particular truck. On this truck that have flaws, just using the wording of the problem. So that is our parameter that we define. So never put P hat up in here and never put X bar. It's always either mu or it is P. So let's go ahead and write that definition down for our terminology. So our null hypothesis is just whatever is claimed. Whatever is claimed in the problem. Whatever is claimed or status quo, whatever has previously been true, in other words, no difference. There's no change in essence. And so it is always going to look like this. It's always going to be H sub 0, and then it's going to be equal P equal to some number, some proportion, and then in section 2, that'll be this is section 8 to, or section 9. We're in section 9 now. We're in chapter 9. So 9 to, and in section 9.3, it's going to be this. It's going to be mu is equal to some number. Okay, so that's always going to look like that. The alternative hypothesis is what you suspect may be true. What you suspect may be true, or what would call for a change, or what would make a difference. What would make a difference? All right, and the way that one is the notation for that is H sub A, and it's going to be that P is either greater than or less than some number. And then for section 9.3, it's got our alternative H sub A is going to be mu is either going to be greater than or less than some number. Okay, and of course always define what P or mu are in the problem. So those are our null and alternative hypotheses. Now, what a one-sided test is this? A one-sided test is when your alternative is either greater than or less than. In other words, your alternative in the section 2 would be that P is greater than something, or that P is less than something. That is going one-sided. We'll talk about that when we do our mechanics as well. And then the two-sided test is when it doesn't say in the problem greater than or less than, it's just going, is it different? So our alternative is going to be when P is not equal to. In other words, it doesn't clearly say that, oh, we suspect the proportion is greater than, or we suspect the proportion is later than, or is less than. It just says, hey, we want to test to see if something is different. Okay, so this one is greater than or less than, and this one is just different, so we got to go not equal to. And the result of that's going to happen is that when we find our p-value, the two-sided test is going to have two tails on it. It's not going to be just a greater than like this one, but if this was not equal to, we would have to include the left tail of the same size. So anyway, so that we'll look at examples of that certainly in this chapter. Okay, so let's continue with this. So we've done that. We've done our hypotheses, right, like that, defining our variable. So that's and of course in section 3, this will be a mu, and this would be defining the mu. Now, and then the next section is very similar, and it's really the most involved section in our inferences, and that is to verify our assumptions. A is verify our assumptions, otherwise known as our conditions. And it's really similar to what it has been in chapter 8, and that is sin. It is sort of the same thing. So that is, if you mastered that in the last chapter, there's good news. It's going to be there the whole time. So the S stands for SRS, or random. Really more accurately, random. Did we get our data from random sampling, or do we have random assignment into treatments for an experiment, which that's not going to come around until later in the year. But anyway, so it just like last chapter. So you would say this: it says a random sample was taken, thus random condition is met. Random condition is met. This prevents bias. It prevents bias, and just like the last chapter, and that's always our most important condition, by the way. The I, just like last chapter, is independence. Because we are not using replacement in general when we do sampling, our population has to be big enough to where we aren't significantly changing it when we take these 300 tomatoes out. So what you would say is this: you would say there must be at least 300 tomatoes. There must be, 3,000, sorry, 10 times that. There must be at least 3,000 tomatoes on the truck for our population size to be at least 10 times our sample size. And that's considered standard notation for population size and sample size, so you can just state it like that. And then lastly, normality, and this is really similar to last time, and to the last chapter, and really the last couple chapters. For a proportion, we would have n times p and n times 1 minus p are greater than or equal to 10. Now, we're doing this whole hypothesis test with the logic of this. We're going to assume that the null hypothesis is true. We're going to assume that actually 10% of the tomatoes are flawed, and we're asking what's the probability we would get a sample p-hat as unusual as the one we got, which, by the way, our sample p-hat is going to be, in this case, we got 38 out of 300 that were flawed, and that's equal to 0.126 repeating. So that's more than 10%. The question is it statistically significantly more? Now, so the logic there is assuming the 10% is true, what's the probability we're getting a sample value this unusual? So we're assuming that P is equal to 10%, and so that's what we're going to use here, and that's what is known as our P sub naught. In the last chapter, we used P hat there, because we didn't have a P sub naught. And so, in other words, in the last chapter, we would use 0.126 repeating, which in fact would end up with our number of successes and failures. But in this chapter, we're going to use this value. So that is a bit of a difference that you need to be aware of. And so, in this case, our n is 300, that's our sample size, times 0.1, our P naught, and then 300 times 1 minus 0.1, which would be 0.9. And so that would be 30, and that would be 270. They're both greater than or equal to 10. And so therefore the quickest thing you can say is just, therefore normality is met. Normality is met. The implications of that is our sampling distribution is all possible values of p hat is approximately normal. Okay, but that's the easiest way of saying it. So the verifying the assumptions is certainly really the most involved part, especially once you get used to the mechanics. Okay, now the mechanics are going to be a little bit different in this chapter. In the last chapter, we would just, in essence, make our interval, but we got to show two numbers now in our mechanics. We've got to show what is known as our test statistic. We got to show our test statistic, and we got to show our p-value. Now, the main number is the p-value. It's the test statistic is what is used in essence to calculate the p-value. But with our calculator functions, we don't really have to worry about that. But you do have to show your test statistic. Your test statistic is going to be, and is in essence the number of standard errors that your sample value is from the hypothesized value. The test statistic is how far this is from this in units of standard error, okay, which, 12.7% is certainly bigger than 10%. But how far is it in standard errors? And that's what gives us a better idea there. And so we have what is known as our z-test statistic. And our little formula, and this is on your formula sheet. So it is the next thing in our formula sheet. It's actually right there, right above confidence interval. It is statistic minus parameter over standard deviation of statistic. So our statistic is going to be p hat in this case. Our parameter we don't know, but we're assuming that it's 0.1. Okay? So that is going to be our hypothesized parameter actually. In the standard deviation of the statistic, well, that's really similar to what we had before. It's going to be this number. Whereas in the last chapter we used p hat there, now we use p naught. So that formula ends up being this. Our z-test statistic is going to be p hat, our statistic, minus p naught, the hypothesized value up there, over the square root of p naught times 1 minus p naught over n. And so in this case, what that would end up being, so that would be 0.126 repeating minus 0.1 over the square root of 0.1 times 0.9, which is 1 minus that, over 300. And when you find that number, let's see, it in fact is equal to 1.5396. So it ends up being that. So what that's telling you, it's telling you that our sample value is about 1.5 standard errors from 0.1. And as you recall from looking at a normal curve, which is what we have here, 1.5 standard errors is not that far. I mean, it's pretty decent, but it's not, it's not like 3 standard errors, which would be way out there. So, but to be more exact about it, we need to find our p-value. And so, what our little thing is, what our sampling distribution is looking like here, is you would say, okay, our sampling distribution centered at 0.1, what's the probability we would get 0.126 repeating or more? And the reason we're going or more is because that's where our alternative is. We're suspecting that the true value may be greater than that. This one is the null hypothesis, and this is, we're suspecting it's greater than. If this had been less than, we would go less than on our curve here. So the way we will find that is normal CDF. So we've been finding p-values for a long time now, actually, because normal CDF creates p-values every time you use it, in essence. And so it would be the 0.126 repeating to 0.1, and to infinity. To infinity. That is the lower bound of my shaded region. That's my upper bound. My mean is 0.1, and my standard deviation is the square root of 0.1 times 0.9 over 300. That is the mean of my p-hats. That's the sigma of my p-hats. And when you do that, when you do normal CDF with that, which let me just remind you of that once again, where do you find this? Well, you would go second distribution right above the vars button, and then go to normal CDF like that. And so we are going from, 0.126 repeating, which that, to be more exact, that's 38 out of 300. So I'll just go 38 divided by 300 to get that somewhat exact value to infinity, or you can just put 9 million there or whatever. And then this would be 0.1, And then our standard deviation would be the square root of 0.1 times 0.9 divided by 300. So close our parentheses there. And so we get 0.0618 approximately. 0.0618. And that is sort of the main number that speaks to us on the test, the p-value. So this p-value is in essence the probability that we would get a sample value this unusual, assuming the null is true. In other words, assuming our sampling distribution really is centered at 10%. In other words, assuming that 10%, it is actually true that 10% of these tomatoes are flawed. That's the probability we get a sample value this unusual. And here is our ending. So our ending is going to be different as well. Of course, with an interval, we would just say, we're 95% confident that, our parameters in there. But our ending now is going to be our p-value statement. We are going to apply this. And there's three things we have to say in our ending. Number one, is our p-value greater than or less than our alpha? Our alpha is a preset value that if your p-value is below it, you reject it. And if you aren't given one, just use 0.05. But you could be given an alpha value of 0.01 or 10% or 8%, whatever. But we'll use 0.05, and that's the one that's used most of the time. Number two, so you've got is your p-value above or below that? Number two is, do you reject or fail to reject the null hypothesis, okay? If your p-value is below 0.05, you reject the null. If your p-value is above 0.05, you fail to reject. You never accept the null. Never accept the null. You're either rejecting it or fail to reject it, and we'll explain that more later. And then number three is that do you have convincing evidence is the good terminology here for the alternative. And then it's very critical at this point that you say the alternative in context. Okay? So that is what we're going to write in our little ending, and we're going to try to get good at. And so in this case, this would be a proper way of writing this. And so our ending would be this. This p-value, which is 0.0618, is less than 0.05, okay? Thus, I reject the null hypothesis, okay? So good Lord, I just said that backwards. Good. Breaking news, 0.06 is actually greater than 0.05. Sorry. So I fail to reject. Sorry about that. Okay. This p-value is greater than 0.05, thus I fail to reject the null hypothesis. Okay, so that is our first. If your p-value is less than 0.05, you reject. If the p-value is greater than 0.05, you fail to reject. Just remember, if the p-value is low, you're going to reject the null. If the p-value is high, you fail to reject it. Thus, we have convincing evidence for the alternative. Convincing evidence that, and then you restate the alternative in context. Our alternative is that P, the proportion of flawed tomatoes, is greater than 10%. So you're just going to restate that in context. That the proportion of all the tomatoes on the truck that are flawed is greater than 0.1. That is how you do a hypothesis test. And this p-value statement, we're going to be stating it the rest of the year. We're always going to be comparing it to the alpha. If it's less than the alpha, we reject the null and have convincing evidence for the alternative. So that's what we got here. So we get a low p-value, so we reject the null. We reject that it's 10%. All right, and that means that we have convincing evidence for this. We have convincing evidence that it's actually greater than 10%. So as far as this other, all right, let's define these other terms here that we have. And Okay, so our other terms, what I just did was effectively a problem from section 8.2. The main thing in 8.1 is defining these terms, but in order to properly define these terms, I feel like you kind of need to see a test. So our test statistic is the number of standard errors, in effect, standard deviations, that our sample statistic is from the hypothesized value. Hypothesized value. So in section 2, it is going to be z, and the formula for it is p hat times p naught, the hypothesized value, over the square root of p naught times 1 minus p naught over n. So that is our formula for our test statistic. In section 3, it's going to be t. So we get t. Our statistic there is x bar minus mu sub naught, our hypothesized value there, over the square root, and then it'll be s over the square root of n would be our standard error there. So that is that we're going to be working with. A p-value. So a p-value, and the p stands for probability. It is a conditional probability, and it's what we've been finding every time we use normal CDF or something like that. The p-value. It is the probability of getting a sample value this unusual, assuming the null is true, assuming the null hypothesis is true. So it is a conditional probability. It's the probability that given that the null is true, it's the probability we're going to get a sample value this unusual. And if the p-value is really low, in other words, if this sample value is really unlikely, assuming the null is true, it gives us evidence to reject the null and have convincing evidence for the alternative. Statistically significant means this: your p-value is below your alpha value. The alpha value, which there's the little symbol for alpha. Statistically significant just means there's such a big difference is that it's unlikely to happen by chance or just by sampling variability. So there we go. Now, the last thing that we want to talk about is type 1 error. Now, whenever you have a null hypothesis and you reject it, the problem is you could be wrong. It could happen, like in our little test we did here. Well, we did not reject the null, but it could have very well been true that the proportion of tomatoes was actually greater than 10%, in which case we would have been wrong here. All right, is that what we said was, well, we got 12.67%, but that's not statistically significantly more than 10%. 10% is still plausible. It's not evidence for it. It's just 10% is still plausible. But we have types of error that we're going to be looking at different examples of type. All right, type 1 error means this. Type 1 error occurs if the null is true, if the null hypothesis is true, but I reject it because I just by chance got a low p-value. But hypothetically, if the null is true. All right, type 2 error is this. So type 2 error occurs, it's sort of the vice versa of that, is when the null hypothesis is false, but I fail to reject it. We never accept anything, in essence, a hypothesized testing. We either reject it or fail to reject it. Here's the little thing that I do to memorize this. Whenever I encounter a type 1 or type 2 error problem, we'll be looking at examples. All right, I remember this phrase. So I've memorized this phrase, is that 1 is hot. 1 is hot. Now, what does that mean? That phrase, 1 is hot, is telling me this. Type 1 error is when the null is true. So 1 is hot tells me type 1 error is the null is true. And it's an error, so I must have rejected it in order for it to be an error. Now, type 2 error is the vice versa of that. So in type 2 error, it means the null must be false. So in type 2 error, the null is false. And it's an error, so I must have failed to reject it. So, anyway, so in this case, we might have committed type 2 error. But we'll be looking at some more examples of that. I wanted to show you one example of type 1 and type 2 error, and hopefully to demonstrate that concept. And that'll be it for section 1. So this says this. All right, the owner of an ice cream shop is considering buying a new soft serve ice cream machine. He has determined that if more than 60% of his customers buy the soft serve ice cream, he'll make a profit from it. He takes a random sample of his customers to try to gauge their interest. If he has statistically significant evidence at alpha is equal to 0.05, in other words, if he does a test and he gets a p-value below 0.05, that more than 60% of his customers would buy soft serve ice cream, he will get the machine. State the null and alternative hypothesis and describe type 1 and type 2 error and the consequences of these two types of errors. So what we've got here is that our null hypothesis is just, in essence, the status quo. So our null hypothesis is just going to be that exactly 60% of the customers will buy the soft serve ice cream. All right, but now, and so that is sort of our status quo. That is the claim. The alternative is what we suspect might be true, or what we're testing for, or what would call for a change or significance. And what it says here is if he has statistically significant, then more than 60%. So that's what we're suspecting. And so there is, in essence, our hypotheses. Now we're asked, what is type 1 and type 2 error? Of course, we would define P over here, which that's important to do in your hypotheses, but I'll do that in a minute. All right, so whenever you're asked type 1 error, I say, okay, I always say to myself this. I always say 1 is hot. 1 is hot. So what that's saying is in type 1 error is when the null is true. And since the null is true, in order for it to be an error, but I rejected it. And so in type 2 error, is sort of the vice versa of that, is the null is false. And it's an error, so I must have failed to reject it. But I failed to, we never accept, I failed to reject the null. So in this case, what we would say is, all right, type 1 error means the proportion really is 60%, but I rejected that. I said more than 60%. So the consequences of that up here would mean that the owner would buy that new machine thinking he's going to have more customers and potentially lose money because he bought the machine and he shouldn't have. Type 2 error means the null is false. Okay, the null is false, but it's an error, but I failed to reject it. I said, well, the actual number is 60%, but I said that it's great, but I made that mistake. So the conclusion is this. Type 1 error is when the null is true. Thus, exactly 60% of the customers will buy soft serve ice cream, but I say that more than 60% will do this. This means that the owner will buy the machine, but will have less customers than anticipated, and he'll lose money. Type 2 error, all right, so in type 2 error, the null is false, and so it was actually true that 60%, would use the machine or would buy the ice cream. So type 2 error is when more than 60% will buy the soft serve, but we wrongly say that 60% or less will buy the soft serve. This means that the owner will not buy the machine and will miss out on an opportunity to make money. So so that's sort of a preview of the whole chapter. We'll be practicing all this throughout the chapter. Section 2 is in essence doing this mini essay. Section 1 is just really defining those terms and introducing those terms to you. And then section 3 is we're going to do this exact same thing with means. So I wish you happy hypothesis testing, and thank you for watching the video.